So I've gone ahead and drawn the circuit from the in-class assignment problem for today, so that I don't have to flip back and forth between screens and all that kind of jazz. I just realized that I forgot to indicate the inductor values here. So let me throw some extra stuff on here. This is a 3 Henry inductor. This guy is a 1 Henry inductor, and it looks like I forgot 2 resistors as well. So we have a 6 ohm resistor here and a 12 ohm resistor here. So our ultimate goal in this problem is to solve for the voltage drop across the current source as a function of time. That being said, this is a first order RL circuit because there's a switch, so it's definitely a transient analysis problem. It's an RL circuit because there are resistors and inductors, and it should be a first order problem because it looks to me like we can combine those 2 inductors into a single equivalent inductance. So just to further explain that a little bit, I'm going to take a look at some of the nodes. I'm not going to bother going through the whole thing here, but we can see that we have this node here in the center, right, and then we have this node in blue that I'm going to put kind of along with outside edge like so. Well, just for the sake of argument, let me extend it all the way. So both inductors are between the red node and the blue node, which means they are in parallel. And so we could combine them into a single equivalent inductance. And that single equivalent inductance is going to appear between the red node and the blue node. Because inductors in parallel combine like resistors in parallel, we're just going to have 1 in parallel with 3, which looks like 1 times 3 over 1 plus 3, or 3/4. So what I'm going to do here is I'm going to erase these 2 inductors, and I'm going to replace them with a single inductance placed between the red node and the blue node. So this is going to be 3/4 of a Henry. And while we are not explicitly asked for it, we are going to need to pay attention to the inductor current at least at T is equal to 0 minus in order to solve this circuit. So I'm just going to call this IL of T like so. And now we've simplified the circuit as much as we can before we actually start our analysis here. Okay. So our first step is going to be analyze this circuit at T is equal to 0 minus. T is equal to 0 minus. Our switch is open and we are at DC steady state, meaning that our inductor will look like a short circuit. Here's our 10-volt source. Ohm resistor, short circuit here. 5 amp source over which we have a voltage VCS at 0 minus. Four ohm resistor there. I'm going to draw my short circuit for my inductor, which is just going to be this diagonal path here. This is IL at 0 minus. Here's my 6 ohm resistor. And here is my 12 ohm resistor like so. And before we get into analyzing this, we can make a couple of observations. So the first observation that I'm going to make is that the 6 ohm resistor appears with the 12 ohm resistor. It also kind of appears to be in parallel with the 12 ohm resistor. But what we really are concerned with is the fact that we have this short circuit here representing our inductor. So effectively, the 6 ohm resistor and the 12 ohm resistor should not contribute to anything. Yeah. So I am going to just put X's here to indicate that they are effectively shorted out by the inductor and won't contribute to anything. And so now we are able to analyze this circuit in a simpler form. So do either of you gentlemen have any suggestions as to the type of analysis that I could or should do here? All right, well, I am going to choose to do mesh analysis here. So let me explain briefly how I came to that decision, okay? I'm going to identify some nodes just really quickly. So that's one node. This is another node. And this is my last node here. So I can see that the 4 ohm resistor, the one in the middle of the circuit, is between the red node and the pink node. And the 5 amp source is between the red node and the pink node, which means they must share the same voltage drop. So effectively, let me do this in a different color actually. The voltage drop across this 4 ohm resistor is going to be the exact same thing as the voltage drop across my current source. Sorry, click the wrong button on my stylus. And we can see very easily by inspection that Ohm's law, 4 ohms times IL at 0 minus, will give us this particular voltage drop. So by employing mesh analysis, I can solve for IL at 0 minus in a pretty straightforward manner. And then I would just use Ohm's law to solve for VCS at 0 minus. So that's why I'm choosing to do mesh here. So my first mesh is going to be this guy up here. Let's call this I1. My second mesh will be this guy down here. I don't have any dependent sources to worry about. So I don't have any controlling variable relationships to write. I do have a current source, so I'm going to have a current relationship equation. So that'll be 5 amps is equal to I2 minus I1. Give me just a moment to restart this program, or that menu is going to keep popping up. Let me save this. And now I'm going to write a KVL equation around my super mesh 1, 2. So starting at the bottom left-hand corner of the circuit, I'm going to have negative 10 volts plus 4 ohms times I1 plus 4 ohms times I2 is equal to 0. And I'm going to solve this system for I1 and I2. So let me grab a calculator here. So this is a 2x2 system. My coefficient for I1 in my first equation is -1. My coefficient for I2 in my first equation is +1, and my constant term is 5. In my second equation, my coefficient for I1 is 4. My coefficient for I2 is 4. And my constant term will be +10 when I move it over to the other side. Solving this system, I get I1 to be -5/4 of an amp and I2 to be 15/4 of an amp. And I can see that VCS at 0- is just 4 ohms times I2 or 15 volts. Another thing, just while we're at it, is that I2 is the same thing as IL at 0-. So how did we feel about the analysis done for this part? Anything particularly crazy or confusing?
I guess just getting started is the main point, because yesterday was all just using simple KVL, KCL stuff, whereas today we're actually using mesh or nodal.
Yeah, this circuit is a little bit more complicated. And because it's a little bit more complicated, we have to use a little fancier technique. So we could have used nodal and mesh in our class meeting yesterday, but as I hopefully illustrated, there were easier ways to do things. For this particular problem, I don't know that there's an easier way to do it, unless, of course, we tried doing something like superposition, where we would wind up solving the circuit twice, which wouldn't be necessarily difficult, but it would definitely be tedious, which is why I chose to just do mesh here. Trying to think. Yeah, simple KCL relationships wouldn't work here, and mesh is nothing more than just 2 applications of KVL in this case. So anyway, all right, so let's look at what's going on at t is equal to 0 plus. So at t is equal to 0 plus, my switch is now closed. So let's start by drawing that portion of the circuit. So here we have our 10-volt source. Our top left 4 ohm resistor. Our central 4 ohm resistor. We're going to have a short circuit across the top here. Here's our 6 ohm resistor. Actually, that shouldn't be a short circuit right now. We'll get to what that is in a moment. My apologies for that. Here's my 5 amp current source. cross switch, we have the voltage VCS at 0 plus. This should be this diagonal bit here. Should be a current source because we replace our inductors at t is equal to 0 plus with current sources having the same direction as our inductor current and also the same magnitude. So that was 15/4 of an amp. And then over here, I'm going to have my (12 ohm) resistor. And I just have this short circuit across the bottom. Like so. All right, so since I'm trying to solve for a voltage and this particular circuit looks a bit daunting, I'm going to employ nodal analysis here. So I'm going to identify my nodes. So we have this guy. This guy. This guy. And this guy. I'm going to choose to put my reference node at the bottom node, like so. And I'm going to call this V1, V2, and V3. And hopefully we can see by inspection that V2 is the exact same thing as VCS at 0 plus. So by doing nodal analysis for this particular circuit, we'll be able to figure out what our quantity of interest is in one step. That one step is doing the nodal analysis. Okay. So no dependent sources, so no controlling variable relationships. We do have a voltage source. So we're going to have a voltage relationship equation that is simply V1. Not sure why my stylus isn't writing. Is equal to 10 volts. Then we're going to write a KCL equation at node 2 and a KCL equation at node 3. So for our KCL equation at node 2, let me indicate which currents I'm adding together. So I'm going to have this current, this current, this current, this current, and this current are adding together. 5 terms in total. The current flowing to the left through the top left 4 ohm resistor is going to look like V2 minus V1 over 4 ohms. The current flowing down through the current source is negative 5 amps. The current flowing to the right through the central 4 ohm resistor is going to be V2 minus V3 over 4 ohms. The current flowing down through the 6 ohm resistor is going to be V2 minus V3 over 6 ohms. And then my current flowing down through my 12 ohm resistor is just going to be V2 divided by 12 ohms. Set this equal to 0. Now I'm going to write a KCL equation at node 3. So that is going to be this current up, this current to the left, and this current diagonally down and to the right. So the current flowing to the left through the central 4 ohm resistor is going to look like a V3 minus V2 over 4 ohms. the current flowing up through the 6 ohm resistor is going to look like V3 minus V2 over 6 ohms. And lastly, I'm going to add my inductor current of 15/4 of an amp. Set this equal to 0. And now I will solve this system. V2 and V3. So this is a 3 equation, 3 unknown system. In my first equation, my coefficient for V1 is 1, my coefficient for V2 is 0, my coefficient for V3 is 0, and my constant term is 10. In my second equation, my coefficient for V1 is -1/4. My coefficient for V2 is +1/4 plus another 1/4 plus 1/6 plus 1/12. My coefficient for V3 is -1/6. And my constant term will be +5 when the 5 amps gets moved to the right-hand side of the equal sign. In my third equation, my coefficient for V1 is 0. My coefficient for V2 is -1/4 minus 1/6. My coefficient for V3 is 1/4 plus 1/6. And my constant term will be -15/4. Solving this system, I get V1 is 10. V2 is,
At 45/4.
yeah, I got 72/7. That doesn't sound right to me. So let me revisit my system and see what I put in correctly, because what you had sounds much better. Should be, I think, like 11 1/4 or something like that. So let me just run through this really quickly. 1 0 0 +10. 1/4 plus 1/4 plus 1/6 plus 1/12 negative 1/6 +5 0 -1/4 minus 1/6 1/4 plus 1/6 -15/4. Still showing up oddly in my calculator. Dave, what did you say that answer was?
I got 45/4 for V2.
All right,
I got
45
9/4 for V3.
and 9/4 for V3. Yeah, I'm not sure what I'm fat fingering in my calculator, but something is being odd. This 45/4 or 11.25 is what I remember from solving this problem previously. So I'm going to go with you being right and me making a mistake in my calculator, just based on my memory here. As I mentioned above, this is the same thing as VCS at 0 plus, which is actually what we were trying to find. So nodal analysis got us what we were looking for without any extra work. Now we're going to move along to step number 3, which will be to analyze the circuit at t is equal to infinity.
One it is again that we don't have to do T at infinity.
So if there are no sources connected to our energy storage element, then we don't have to worry about dealing with things at t is equal to infinity. So if we look at our circuit, our original circuit, our switch does nothing to remove the 10-volt source or the 5-amp source from influencing the behavior of the inductance here. So that means we're definitely dealing with a total response problem. Only when the switch disconnects sources from the energy storage element will we be able to neglect what's going on at t is equal to infinity. And we're not really neglecting anything. We just understand that all of our signals will settle to 0 at t is equal to infinity. Just as a quick aside type thing, if you look at the practice exams and things like that I gave you, effectively, I don't tell you whether you have a natural response problem or a total response problem, but you will notice that if it's a total response problem, I will ask you about what's going on at t is equal to infinity. And if it's a natural response problem, I won't. So the way that I make the test problems is effectively going through the circuit step by step using these exact steps. And when that analyze the circuit at t is equal to infinity doesn't actually give us anything useful, I, generally speaking, don't include it. All right, so at t is equal to infinity, our switch is still closed. But now we are once again at DC steady state, which means that our inductor is going to look like a short circuit again. So here's our 5-amp source. This is VCS at infinity. Our 4-ohm inductor, short circuit. Excuse me, 4-ohm resistor, short circuit, 6-ohm resistor. This short circuit here represents our inductor at t is equal to infinity. And then we have our 12-ohm resistor over here. So once again, I am going to use nodal analysis here, just because I'm trying to find a voltage and this circuit looks complicated enough to justify it. So identifying my nodes. Here's one. Two. And 3. So this looks like we're going to have a 2x2 system. Choosing the bottommost node as my reference. Here is V1 and here is V2. I'm going to have a voltage relationship equation that is V1 is equal to 10 volts. And then when I perform KCL at node 2, I'm going to be adding this current, this current, this current, this current, and this current together. That's going to look like V2 minus V1 over 4 ohms minus 5 amps plus V2 over 4 plus V2 over 6 plus V2 over 12 is equal to 0. I'll now solve this system. Hopefully I can make my calculator work correctly this time. So I have 1, 0, and 10. And then I have -1/4. And then 1/4 plus 1/4 plus 1/6 plus 1/12 is equal to +5. I get 10 volts for V1 and 10 volts for V2, where V2 is the same thing as VCS at T is equal to infinity. Now we move.
Got the same thing.
Okay, great. So I didn't make a mistake this time. That's good news. So now we're going to move along to determining the time constant for our circuit. So that's step number 4. Determine tau during the transient condition. Because this is an RL circuit, we know tau should be LEQ divided by REQ. And we already found at the beginning when we simplified things that LEQ was 1 Henry in parallel with 3 Henries, or 3/4 of a Henry. So to find our equivalent resistance, we will redraw our original circuit during the transient condition. So that means with the switch closed. And the conductor is going to go here. Now, I'm finding the Thevenin equivalent resistance with respect to my energy storage element. So I take that inductor out. I look in through the terminals left behind. And because I'm finding the Thevenin equivalent resistance, I need to be looking at a dead network, which means that my 5 amp source is turned off, replacing it with an open circuit. My 10 volt source is turned off, so I replace it with a short circuit. And so now I have this network. Since this isn't obvious to me, I'm going to use the resistor combination techniques like we've detailed in class. So I'm going to identify my nodes. So this is one node. This is a node. And let's do this one in green. This is a node. I'm going to label these nodes. Let's call the green A, the blue B, and the red C. And let's scroll down here so we can do my regular resistor combination technique. I'm going to put A on the left-hand side of my page, and B, since this isn't very big, I'll just put it over here. I think this will be plenty of room. So there is no direct path from A to B. So when I leave node A, my only choice is to go to node C. And I can either go through the 4 ohm resistor in the middle, or the 6 ohm resistor. To go from node C to node B, I can either go left through the 4 ohm resistor or right through the 12 ohm resistor. So the equivalent resistance then is going to be 4 in parallel with 6 in series with 4 in parallel with 12. So 4 times 6 over 4 plus 6 is 2.4, or 24 over 10, which would be 12 fifths. And then 4 in parallel with 12 is, let's see, 48 over 16 is 3. By all means, feel free to use your calculators for this. So let's see, so that's 15 plus 12 is 27. Fifths of an ohm. Let me just actually throw this into my calculator and make sure I'm not making some sort of dumb mistake.
That's what I got too.
Okay, well, if that's what you got, then I'm gonna leave it as that. And so we have 3/4 of a Henry divided by 27 fifths of an ohm. So that's going to be 15 over, let's see, 4 times 27 is going to be 108. Um, 108 is divisible by 3. No.
5 over 36. So I got.
Oh, 5 over 36. I was right with 36 there. Okay. And from this, the inverse of our time constant is 36 fifths per second. Now we're ready to wrap things up, which brings us to step number 5. Plug stuff in to our generic equation. So the generic equation, to remind you guys, is y total is equal to y at 0 minus or t less than 0 minus. And it will be y at 0 plus minus y at infinity e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. So VCS of t will be, so y at 0 minus, or VCS at 0 minus was, if I'm remembering correctly, 15 volts, but let's just check here. Yep, so 15 volts. T less than 0 minus. Y at 0 plus was 45 over 4. Y at infinity or VCS at infinity was 10. So 45 over 4 minus 40 over 4 gives me 5 over 4. E to the negative, the inverse of tau, so 36/5 t plus y at infinity, which was 10 volts. T greater than or equal to 0 plus. And this matches the provided answer on the in-class assignment sheet. So, Dave, you pointed something out much earlier on, that this problem was significantly more difficult than any of the examples that we had worked in class thus far. Quite true. I believe that this particular problem is significantly more difficult than anything that I have put on a test. That's not the case, but I've provided you with old tests to work and all that kind of good stuff. So what do we want to talk about now?
If I remember right, you mentioned that these types of problems were going to be most of the exam.
I don't know that I would say that it's most of the exam, but it is a significant portion of the exam. Okay. So let's talk about what's going to be on the exam. I'm literally going to kind of spell things out for you. Okay.
That would be great. Thank you.
Problems 1 through 5 are theory questions. So I might ask you a conceptual question about the concept of inductance, or the concept of capacitance, or the concept of Thevenin and Norton equivalent circuits. I might also ask you about relationships between, voltage and current for capacitors and voltage and current for inductors. So very similar in nature to what you saw on exam 1 with regards to theory questions, just general conceptual questions, no circuit analysis whatsoever. Okay. Problems 6 through 10 will be regarding Thevenin and Norton equivalent circuits. So 6 and 7 will be a circuit that does not contain any dependent sources. And I will ask you to determine 2 of the following quantities: Thevenin voltage, Norton current, or Thevenin resistance. Problems 8 and 9 will be a circuit that does contain a dependent source. And I will ask you to find the Thevenin voltage and the Norton current. Problem 10 will be a network that does not contain any independent sources, so only dependent sources and resistors. And I will ask you to use the test source method to determine the Thevenin equivalent resistance. I will not say use the test source method, but that's literally the only way to solve it. So I'm giving you a very, very strong hint, if you can even call it a hint, because I'm telling you directly what to do. Use the test source method for problem 10. Okay. Let's see. So 11 through, let me think about what number I should get up to here. We'll figure that out in a minute. Let me go backwards, actually. So 21 through 25 will be a total response problem. That means that 20 will be the last problem for a natural response problem. So let's see, 20, 19, 18, 17. Which means 11 through 16 will be capacitor, inductor related. All right. So for the capacitor and inductor related problems, here's the type of things that you should expect. A circuit, a DC circuit where I ask you to calculate the energy stored in a capacitor and or an inductor. Very similar to homework problems. Probably something with a graph. That will be either the voltage drop across a capacitor, the voltage drop across an inductor, the current flowing through a capacitor, or the current flowing through the inductor. And based on that graph, I expect you to be able to give me 1 to 2 different things. So like power or energy or current or voltage, very similar to in-class assignment problems and homework problems. There might be something similar to homework 12 number 3 or homework 12 number 5. I'm probably just going to make that one question, and it will be, in my opinion, the hardest question on the exam. Not because it's going to take a whole heck of a lot of work, but it requires you to understand all of the relationships that we've dealt with for this particular period. I took the time to not fully work through homework 12 number 3 and homework 12 number 5, but I did give you very, very strong hints in that lecture video associated with that material. So review that if you feel the need to. And then if there's anything left over, you might have a inductor combination problem or a capacitor combination problem. 17 through 20 is natural response, 21 through 25 is total response. So it looks like 9 of the 20 questions involving actual analysis will be on this transient analysis material. So not quite half, but pretty close. So I've told you what's going to be on the test. What more do you want to know?
Could we maybe work an example of we did the total response today. Natural response or total response is just a continuation of natural response. Maybe an example of one of those more difficult.
Right, the total response problems are not necessarily more difficult, but where you're going to have a non-zero value, or you may have a non-zero value at t is equal to infinity, would be a better way to put it.
Yeah, okay.
So yeah, total response problems, and you'll know it's a total response problem because I ask you about what's going on at t is equal to infinity. The natural response problem, I'll just ask you what's going on at 0 minus, what's going on at 0 plus. Give me the time constant and then plug stuff in. The total response problem, I'll ask you what's going on at 0 minus, what's going on at 0 plus, what's going on at infinity, the time constant, and then plug stuff in.
Okay. I guess if we could work one of the more difficult capacitor inductor questions, that might be helpful.
All right, let me look at an old test here and see if I can find something. Like I said, these are going to be usually based on something very similar to homework 12 problem 3 or homework 12 problem 5. So let's see if I asked anything in fall of 2020 and 2. All right. So this is from the fall of 2020. I honestly do not remember whether or not you guys have access to this test. This is the question that I asked. So you have a voltage source, Vs of t, connected in parallel to a capacitor connected in parallel to an inductor. I specified that our capacitor current IC of t is flowing down. I specified that our inductor current IL of t is flowing down. And I called this current across that top right there, IS of t. And I tell you that Vs of t is equal to 68 e to the minus 52 t millivolts. And Is at 0 is equal to 32 milliamps. For problem 19, so it looks like I asked 2 questions about this particular circuit. For this test, I don't expect to ask 2 questions about it on the upcoming exam, just to be clear. I ask you to find IC at 7.2 milliseconds. And I ask you to find IL at 8.4 milliseconds. Okay. So this was number 19 and number 20. And this was back when I was still giving, I think, 3-hour exams or something like that. So, all right. So let's work on number 19 first, because it's the easier of the 2. Okay. So what's the relationship for if we want to determine capacitor current and we know capacitor voltage? So which relationship should I be using? That's one of the hard parts, knowing which relationship to use. So what I'm going to do here is I'm going to write down all 4 relationships that I expect you to know for capacitors. So we have our derivative-based relationship that says I is equal to C dV by dt. We have our integral-based relationship that says V is 1 over C times the integral from T naught T of I dt plus V at T naught. We have power relationship that is I times V or C V dV by dt. And then lastly, we have our energy relationship, which is 1/2 CV squared. So let's number these. 1, 2, 3, and 4. Which number am I supposed to use here?
My guess would be 1.
Your guess is correct. I know what the voltage is and I'm trying to find the current, so I would use relationship 1. Okay. So using relationship number 1, I could say that IC of T is equal to C, which is 23 millifarads. And a milli, excuse me, so the milli is 10 to the minus 3. A farad is an amp second per volt times the derivative of my voltage, where the derivative of my voltage is going to be 68 times 10 to the minus 3 volts times negative 52 per second e to the minus 52 t. And if we look at our units here, this volt cancels this volt, this per second cancels this second, and so we're just left with amps. So let me just throw this into my calculator. 23 times 10 to the minus 3 times 68 times 10 to the minus 3 times negative 52 is going to look like negative 81.328 e to the minus 52t milliamps. And now we would just plug in the value for t that we're trying to find things at, 7.2 milliseconds here. So IC of 7.2 milliseconds is, let's see, answer times e to the negative 52 times 0.0072. I get negative 55.929 milliamps.
So when I chose 1, I chose it because on 19 we were looking for current, and then based on these 4 relations, that was the only one that defined current. But then, oh, okay. I guess the deeper question I have is, like, what other relationship should I look for? Because you said because we have the voltage and the capacitance, that would be what we look for.
So I said we're trying to find current and we know the voltage. So if we're trying to find current and we know the voltage, well, if we know the voltage, taking the derivative of the voltage is straightforward.
Right.
So for the second expression here, this gives us voltage in terms of current, so that if we knew the current, we could take the integral of the current in order to effectively find the voltage.
I see. Okay.
So effectively, the quantity on the left-hand side is what we're trying to find, and the quantity on the right-hand side is the things we know.
Okay. And then so for 3, we want to know power. And then it looks like I could define it 2 different ways. We either have the current and the voltage, or the voltage, well, just the voltage.
Right.
And then for 4 it would also be just voltage. But then that would be energy. Okay.
Yep.
Cool. Okay.
All right. So for number 20, we're trying to find inductor current, right? So I'm going to write down my inductor relationships down here. These are going to be extraordinarily similar. Stylus will stop quitting in the middle of writing things. So the first thing I'm going to have is my derivative-based relationship. that says V is equal to L di by dt. Then I'm going to have my integral relationship. I is equal to 1 over L times the integral from T naught to T of V T prime dt prime plus I of T naught. Then I have my power relationship. So this is just I times V always, or I could express it as L I di by dt. And lastly, my energy relationship. 1/2 L I squared. So I'm trying to find current and I know voltage. Which one do I use?
2.
Exactly right. So using relationship number 2, we would have IL of T is equal to 1 over L, so 1 over 47 millihenries. So that's going to be 47 times 10 to the minus 3 volt seconds per amp. Close this off here. Times the integral. So when I integrate, I'm going to pull down a factor of 1 over negative 52 per second. The 68 millivolts is going to be in the numerator. So 68 times 10 to the minus 3. And then I'm going to have my e to the negative 52t. And then I also have plus IL at T naught. I'll write down like this. Okay. So I can simplify all that numerical stuff on the top here. So the times 10 to the minus 3 cancel each other out. This volt cancels this volt, this per second cancels this second. So I have just units of amps. So 68 divided by 47 times negative 52 gives me negative 27.823 e to the minus 52t plus IL at T naught milliamps. So I now need to figure out how to determine IL at T naught. And we're going to do it exactly like we did in the homework problem, right? So let me scroll up here. So if we apply Kirchhoff's current law to this network, we can see that IS of T is equal IC plus IL. We can extend this out to say that IL at 0 is just going to be IS at 0 minus IC at 0. IS at 0 was given to us as 32 milliamps. IC at 0 is negative 81.328. Milliamps. Just to be clear, I'm getting that number from this part. So at T is equal to 0, the exponent bit goes away. So 32 plus 81.328 comes out to be 113.328. And now I would simply plug in my value for time, right? So IL at 8.4 milliseconds is going to be 113.328 minus 27.823 multiplied by e to the negative 52 times 0.0084. And I got that to be 95.351 milliamps, which actually isn't the thing that I have highlighted. So I want to figure out my process is right for sure, but I want to make sure I didn't make a mistake here. So 32 minus negative 81.328. And then let me see here. So 68 over 47 times negative 52. $27.823 E negative 52 times 0.0084 plus yep 95.351. So this problem was effectively almost identical to homework 12 problem 5, except that I broke it up into 2 steps as opposed to just asking you for the final answer like it did in that particular problem. The other variant of this would be instead of everything in parallel, it would be multiple things in series, which is homework 12 problem 3.
And just to make sure, when they're in series, you treat them like resistors in parallel. Is that right?
No. So let me clarify what I believe you are asking. So whenever we have inductors in series, they combine like resistors in series. Whenever we have capacitors in series, they combine like resistors in parallel. Now, what I am referring to, homework 12, problem 3, is a circuit that contains, I believe, a current source in series with an inductor in series with a capacitor. You cannot combine inductors and capacitors, or at least we don't know how to do that yet.
Okay. All right. Thank you. And then I was looking on the fall 2020 exam, the problem 16 set. It's just a graph one. But the solution was I couldn't quite make out what was going on. I don't know that we have to work it out. Or I mean we could, but
yeah, let me open it up.
Okay.
So let's see. Old tests. Fall 2020, you said?
Yes, that's right.
All right. So we have a capacitor that has a value of 510 microfarads, and we are given the voltage, and we are asked to find the current. So let me pop back over here. We have a capacitor. We're given voltage. We're asked to find the current. Which of those four capacitor relationships am I supposed to use?
2. We're given
Incorrect. We're given the voltage and
Oh.
we're asked to find the current.
1 then.
Yes, 1. So just going to write up here. I is equal to C dV by dt. Well, C is given to us. dV by dt is just the slope. So we're looking for the current at T is equal to 3.875. So what I'm expecting you to be able to do for this particular problem is to determine the slope of the voltage during this interval that I've outlined with these red dashed lines. So effectively, I want the slope of this line. Multiply that slope by 510 microfarads, and you should have your current. So
Okay.
what's the slope?
So it would be 510 microfarads times 0 minus 6 over 4 minus 3. So -6 over 1. So -6.
So 510 times 10 to the minus 6. I'm on board with you there. And then we're going to have 0 minus 6. I agree with that. And we're going to divide that by 4 minus 3. But that 4 minus 3 is in milliseconds. So we need another factor of 10 to the minus 3 there in the denominator to give us the right units. So like numerically, if we didn't do that, we'd be getting like 3.06 kiloamps. So it's not going to really make that much of a difference if you're not paying attention to the units here, but I like to be consistent with the unit. Okay.
Yeah. Okay.
Yeah. So just to be clear, that was 510 times 10 to the minus 6, where farad is an amp second per volt times 0 volts minus 6 volts divided by 4 milliseconds minus 3 milliseconds gives me negative 3.060 amps. For number 17, I'm asking you for the power.
And so then we would use one of those relationships again.
Yep. So we really have an option. Let me go back to the relationships, right? So I'm asking you for the power. So obviously we're going to be using number 3. Okay.
Yeah.
We can use the product of voltage and current, or we can use C times the voltage times the derivative of the voltage, because C times the derivative of the voltage is just the current. So how I generally would approach this one is I would find the current at T is equal to 5.5 milliamps, which means I'm looking for the slope over this interval. So the slope of this line, multiply it by 510 microfarads, and then multiply it by the voltage, which the voltage appears to be negative 4 volts.
And you got okay, and you got that by taking -2 minus -6. I mean, another way you could do it is, of course, just looking at. I mean, like the middle is -4, but just if I wanted to calculate it.
Well, I mean, I would suggest for this one in particular, like if I ask you to find it somewhere in the middle of a thing, I make it to be an obvious thing. So because we know that the slope in this case is going to be, so let's see, it's increasing 4 by 1.
yeah.
So, yeah, so I mean, looking at it, we can see that the voltage is -4 at T is equal to 5.5.
Yeah, okay.
Try not
okay.
to throw you too many curve balls and make you do like linear interpolation or anything like that, because you guys get really mad at me when I ask you to do it, even though you should know how. So try to make those fairly straightforward. So you find the current, just like we did in number 16, multiply by the voltage, and then we have the power. Number 18, I want the energy at a particular time. So that means if I look at my energy equation, all I need to know is the voltage. So I'm just going to read the voltage off the graph. We're looking at T is equal to 2 milliseconds. So at T is equal to 2 milliseconds, looks like we're at positive 3 volts.
Yeah.
So 1/2 times C times 3 volts squared gives me the answer that I'm looking for.
Okay.
So the other variant on this problem would be something like, let's just say for the sake of argument, sorry, I'm trying to erase, not just scribble over everything. If instead of voltage, this were current measured in amperes, how would that change the problem?
That would change which relationships we're looking at.
Exactly right. So instead of doing the derivative-based relationship, we would do the integral-based relationship. So for a problem like that, I wouldn't ask at T is equal to 3.875. I would ask for like T is equal to 3. So that you would literally just be finding the area of this triangle, dividing it by C is equal to 510 microfarads, and then adding the initial condition, which I have to give to you.
Okay.
And so when I'm asking you to do any integration with these things, it's always just going to be simple right triangles and rectangles. So I know that you probably don't need this, but I've definitely had students over the summer who could not for the life of them remember what the area of a right triangle is. 1/2 base times height.
Yep. Okay. Okay. Yeah, that exactly answers our question. Thank you.
I don't know if I mentioned this, but something like this is also a possibility, where I give you a mathematical expression and then ask you for current or voltage, power, and energy. So it's literally just using the relationships directly, not applying them to a graph. And I ask you to do this on your homework sets, or excuse me, in the in-class assignments, and I believe there are homework problems, actually, I know for sure there are homework problems for this as well. Because when I went through the homework sets, I was like, oh, this is just a straight application of the relationships.
Okay.
Yeah. So that's another possibility for the capacitor inductor portion. Generally speaking, I typically ask one problem related to capacitors, one problem related to inductors. And if it's, say, the derivative-based relationship for one, it'll be the integral-based relationship for the other. I don't typically double dip.
Okay. I can't think of any other questions for now.
Yeah, no, that's fine. You've got my cell phone number. It's on the syllabus and all that kind of stuff. You've got my email address, and we have effectively a week, or actually a week and a day before you have to take the test. So if you can think of any more questions, you let me know, and I'll be happy to help.
All righty. Thank you so much for your time again.
No problem.